Okay, good morning, everyone. How did the homework go? Do you have any questions about the homework? 40 and 55. Okay, we look at those. Okay, all right. I read the question. 34 and 37. Okay, so let's look at those first. Use geometry to evaluate the following definite integral. Sketch a graph of the integrand, show the region in question, and interpret your result. So I have the integral from -4 to 2 of 2x plus 4 dx. Okay, and they want me to evaluate this integral by interpreting it. Okay, so what do they mean by that? I mean, today we're going to learn how to evaluate this integral, but now we're going to try to compute it by evaluating it. So this is my function f of x in here, and this is the dx. So how do we interpret that? We're going to graph the function f of x, graph it. So this is f of x equal to x plus 4. Okay, and I want to graph it between the interval -4 and 2. So 2x plus 4, that's a straight line. And I'm going to evaluate correctly. So that's a straight line. I'm going to sketch it. If x is -4, this is -4. This is -8 plus 4. This is -4. And if x is 2, this is 4 plus 4, that's 8. So at -4, I am at -4, right here, let us imagine. And at 2, I am right here. So that's my graph. Okay, that's the graph. All right. Now, what does the integral represent graphically? Graphically, if this is the function f of f, the interpretation is it is minus the area of the region below the x-axis plus the area of the region above the x-axis. So the graphical interpretation of this integral is, so this is equal to minus area of the region below the x-axis plus area of the region above the x-axis. Okay, which we call this area, this is called, it has a name and called net area. Okay, it's not called the area, it's called the net area. So when you have this region like this, you take minus the area below the x-axis plus the area, we call it the net area. Okay, that's the word it's used. So evaluating this integral geometrically is really boiling down to compute this net area. So let us compute this net area, all right? So we need the area of this region. So I'm gonna call this R1 and R2. I'm gonna find each one of them. Now we need the area of R1. Okay, what's the area of R1? What's the area of R1? How can I find the area of R1? What do I need? Anybody? Get back to you. How can I find the area of R1? What is it I need? What's the missing data? R1 is a triangle. That's R1. To find its area, it's the base. It's a half the base times the height. Okay, that's a triangle. Area of a triangle, half the base times the height. So it's -2. A half the base times the height. And the same thing here. Okay. Now, The height is from here to here. And this point right here, this is -4, -4. So the height, which is the actual height, it is 4 in this problem. So I have the base times the height. I have it at 4. To find the base, what do I need? What do I need to find the base? Look at the picture. What do I need? I want answer from you. Come on, how would you need? You need something to find it. What is it you need to be able to find how much you have from here to here? Which point do you need? Are you guys awake? Are you with me? We need to find the x-intercept. Exactly, we need to find the x-intercept. We need this point. But how do we find the x-intercept? We need to set to x plus 4 equal to 0 and solve for x. It's -2. So it means this point right here, this is -2. I need that point to be able to find the area. So now what's the base of my triangle? That's -4 here, that's -2. This base is equal to 2. And that's the base.
I have a question.
Oh, yes, please go ahead.
Could since it's a number graph, could we just count the number of spaces there are in between the -4 and the -2 also?
But you have to find it. You have to know where it is. So if you don't know this is -2, how you can count anything?
Oh, okay.
Right?
All right.
It could be
Yeah.
-3/2. It could be -1/3. I don't know. I have to find it first. Got it?
All right.
Okay. Now, from -2 to 2. Now I want to find the area of R2. Okay, it's a half the base. The base in this case is from here to here. And how much I have from -2 to 2? I have 2 units from here and 2 units. That's 4 units. That's the base. And the height. What is the height from here to here? I need this point. Now, what's this point here? This point was 2. And when I plug in 2 inside the formula, I got an 8 times 8. Okay. So now, but the integral is not, it's the net area. So it's minus this piece. It means -4 plus this piece, which is 16 divided by 2, which is equal to 8. And we get equal to 4. Okay. So that's how we do it geometrically. That's again, the problem is to emphasize the graphical interpretation of the definite integral, which is the net area, which means minus the area below plus the area above, minus below plus above. So it's not this the area, it's minus plus. Right? So let's look at the other problem we assigned. I mean, you're asking for. So number 55. Number 55, what is it? Right here. They want us to use the properties of integral to do a bunch of stuff. So this is the given integral from 1 to 6 of f of x dx. It's 10. Integral from 1 to 6 of g is 5. Integral from 4 to 6 of f is 5. So that's what's given to us. And the integral from 1 to 4 of g is 2. Okay? And I want us to evaluate a bunch of stuff. So we start with the first one, integral from 1 to 4 of 3 times f of x. Okay. Now, one of the property we saw yesterday that if you have a definite integral and if you have a constant, you can move the constant out. Only constant could be moved. Only constant, that's important. If you have a variable, like if you have x here, you cannot touch it. F of x dx. Now we use Okay. All right. Now, integral from 1 to 4 of f, we don't have it because I have from 1 to 6 and I have from 4 to 6 and I want from 1 to 4. So we're going to do exactly what we did yesterday. So what do we have? We know that the integral from 1 to 6 can be split into from 1 to 4 plus from 4 to 6. Okay, we know that. And this is f. Be a bit sloppy here, but I hope you understand. So from 1 to 6, we split it. Now we know from 1 to 6, we know that this is 10. And we know from 4 to 6 that is a 5. So from 1 to 4, that should be a 5 as well. Okay, so it's going to give me 3 times 5, which is equal to 15. Okay. And then the rest actually is the same game. So I will pick one more and then I think it will do. I will pick, for example, C and F. C.
For the 15, would you multiply by 3 as well for the constant that you moved out? Or did you just, oh, never mind, did that already. Okay, never mind.
Fine, sure. Okay. Let's look at C. Integral from 1 to 4 of F minus G. Yesterday I said if you have a sum or a difference, you can split. You cannot split if you have a multiplication. So since it's a difference, I can split. So this is integral of f of x dx minus the integral of g of x. And now I just basically pick those up from 1 to 4. We already figured it out. It's a 5. And minus from 1 to 4, the g is the given to us, which is a 2, giving me a 3. Okay. And now I'll do E, and the rest is actually the same. So that is, I don't think you guys should be able to do them. If you can't, you ask me tomorrow. Integral from 4 to 8 of 8 times g of x dx. Again, 8 is a constant. The constant can be taken out. I will have 8 times the integral, from 4 to 6. From 4 to 6 of g of x dx. Okay. Now, let's see, 4 to 6 of g, I don't have it. So I have to find the integral from 4 to 6. Again, I will do the same thing I did a minute ago. From 1 to 6 of g is the integral from 1 to 4 of g plus the integral from 4 to 6 of g. Okay. From 1 to 6, I have a 5 for this one. And from 1 to 4, I have a 2. So from 4 to 6, this should be a 3. Okay, so now I will have 8 times 3. I will get a 24. All right. Okay, let's look quickly at the last two problems, and then we have to move on. Okay. So I'm going to look at 34 and 37. And if they are verbatim the same, I will actually do one. So 34 and 37. Okay, let's look at 37. And 37 is, and as I told you yesterday in class, the way I want you to interpret that is the limit as n tends to infinity. So instead of having what the book have a delta, I told you just substitute this by n goes to infinity. And well, n, what does n represent? What does n represent? Who can answer the question?
Number of subdivisions.
Absolutely. It's the number of subdivisions. Thanks. Okay. Now I used the subscript, I used I for a subscript. It doesn't really matter. I can use anything I want from 1 to n. Okay. Now don't let the star bother you. The star could represent usually left, right, or midpoint. So let us assume this represents the midpoint. So it doesn't really, this X star, instead in class I used X, I think XK for left, for right, and I use that for middle, for the midpoint. So you can think of that as a midpoint in this problem. So this is, when you see something like that, the idea is we're gonna start building up that's an integral. That's an integral. Integral of what? They tell you of 1, 2. Means what basically doing is that they are taking the interval from 1 to 2. They are splitting it into pieces, and they are adding those quantities. So this is basically what the function f should be. So that's really what's give away the function f. So my function f is x, ln of x, dx, and my interval is from 1 to 2. So what the sum is, basically they are taking the interval from 1 to 2. They are taking the function lx, ln of x, gonna look something like that. So this is x, ln of x, that's the function. And they are starting to subdivide and take the sum of the area of those. That's a positive function. So they are taking the sum of those areas. So that's really what they are doing. And that's what we call the definite integral. So
I have a
finally,
question.
yeah, please go ahead.
Is there anything under X right there or no? Under the X before the ln of X in the answer?
That's multiplication, sorry.
Okay.
It's because that's what it is. You're multiplying x, ln of x.
Okay.
That's the function. That's the function. Okay. And finally, I look at 34. 34 is, they're giving us integral from pi over 2 to 0 to pi over 2 of cosine x dx. Okay. And the question is basically, they want us to estimate. They want us to estimate this integral, use midpoint sum. Okay. Remember, the integral is nothing more than those Riemann sum when the number of subdivision goes to infinity. I mean, gets larger and larger. So here they want us to estimate this integral, but they want us to do it with only 4 subdivision. So that's what the integral is. It's really, I mean, a lot of time when you guys are gonna, the calculators say, evaluate definite integral, and actually the way they do it is basically they do Riemann sum. Even though we're going to learn today a very powerful tool to compute some definite integral, but your calculator and a lot of computer algebra system, and basically they do those kind of sum in a very sophisticated way, of course. They do those kind of Riemann sum to evaluate those integrals. So we're going to do it only for 4 because we basically doing it by hand. So what's the idea here? My interval is 0 pi over 2. 0 pi over 2. My function is, that's my function. So my function here is the cosine of x. So we're going to graph cosine. At 0, cosine x is that. At pi over 2, so that's the cosine, because it's a 0 here. And it keeps going, but we're not interested in it after that, because we're only interested in 0 pi over 2. And I'm going to take 4 subintervals. So this is split it here. 4 equal pieces. And I want me to use the midpoint sum. So I'm going to take halfway here, halfway, halfway, halfway. And in this problem, because the function is positive, it's really going to be exactly the sum of the area of those rectangles. Sorry, this should be dotted. This is dot, that's the height. And that's the height. Okay, so basically in this particular problem, because my function is positive, I'm computing the sum of the area. All right, so the rest is basically we have to pick up to find the delta x. We have to find the coordinate of those points and then proceed. So let us see what the delta x is. From here to here, I have pi over 2. I'm going to divide it into 4 pieces. This will give me pi over 8. Okay, so this is the delta x. That's the link because this is pi over 2. And now we need to find those points. Okay, this is 0. So this is basically pi over 8. Okay, and now let's compute those. This is pi over 8. Basically pi, another pi over 8, 2 pi over 8. So, and this one we're going to give me that's 3 pi over 8, 4 pi over 8. As you guys, we're adding pi over 8 every time. 4 pi over 8, this will give me 7 pi over 8, and this will give me, no, I meant 5, 6, 7 pi over 8. So these are the point of interest too, okay? So now the book is asking you about x0, x1, x2, x3, x4. Basically, the book is asking you about the endpoint. Now, we don't really need them in this problem because I'm interested in midpoint, but let us make sure we know how to do them. X0 is 0. X1 is pi over 4. No, what did I do stupid here? What did I do stupid? You guys should correct me. What did I do wrong? What did I do wrong? What did I do wrong? Anybody? I did something wrong here. What is it?
Should the red dots be pi over 16? Because every interval
Exactly.
is
When I do
pi over
something
8.
wrong, you should scream. You should tell me, you know, I don't understand. Okay, so from here to here, it's pi. So this has to be pi over 16. Okay, pi over 16, 2 pi over 16, 3 pi over 16, 5 pi over 16, and 7 pi over 16. So when I do something that it doesn't make sense to you, you guys are smart. Tell me, you know, it doesn't make sense to me. All right. So this now, this is x1 is pi over 8. X2 is pi over 4. X3 is 3 pi over 8. And finally, x4 is 4 pi over 8 or pi over 2. So these are those points. These are just endpoint. But I want the midpoint. So the midpoint is pi over 16. It's halfway between those. 3 pi over 16, 5 pi over 16, 7 pi over 16. And now what is the estimate? So now this is going to be equal, almost equal to, and that's an estimate. The value of the function at pi over 16 times the delta x plus the value of the function at 3 pi over 16 times the delta x plus the value of the function at 5 pi over 16 times the delta x plus the value of the function at 7 pi over 16 times the delta x. So we're really estimating this. We're estimating the integral. So it's going to give me equal to, what is f of pi over 16? My function is the cosine function. So that's the cosine times my delta x, which is the pi over 8, plus the cosine height times width. Height. The reason I keep writing this because somehow I want the sum to start really sinking in, because it is going to come up all the time with us. Cosine at 7 pi over 16 times the pi over 8. Now the rest is I just need to compute. So now the computation, I can factor out the pi over 8. Only when I compute, I factor it out. And then I will have those sums that we can evaluate. That's that. Okay. Right. Now, one remark that in calculus, we only work with radian. We never work with degree. So whenever I'm giving you any problem, anything in calculus, it's radian, it's never degree. So now the rest is actually simple. We just have to evaluate the sum and you will get a good estimate. So I will do that very quickly. And so it's cosine pi over 16. Now I'm going to start making mistakes because I don't like. So this is going to give me pi over 16 plus, anybody have the answer to that? Plus cosine 3 pi over 16 plus cosine and 5 pi over 16 plus cosine 7 pi over 16. So that's going to give me 7 pi over 16. Okay. And I have to multiply this by pi over 8. So unless if I didn't goof a lot, I got 1.0064. And that's an estimate. It's not the actual value. We're going to compute the actual value in a few, in 10 minutes, but that's the estimate. So that's what is the estimate for this integral. So it means an estimate for this area is 1.0064. And we know it's not the exact value because there are a lot of, we're not getting the exact area, but we're getting very close to it. Okay. All right. So this is really, that's a good, also good problems, which reminded us, this problem remind us is that how to estimate the definite integral by taking Riemann sum. And this problem tell us, helping us slowly to build up that this sum is nothing as it is the definition of the definite integral. And then the previous problems want to remind us that graphically, the definite integral is the net area. It means minus the area below plus the area above the x-axis. So if I'm integrating, in this problem, my function was positive, so I didn't have to do much. In a previous problem, the first problem, when I took 2x plus 4, the function was positive and negative. So the definite integral represented minus this area plus this area. Today, we're going to state section 5.2, what we call the fundamental theorem of calculus. So 5.3, the fundamental theorem of calculus. There are two of them. I will emphasize only one, the one that we will use, you will use all the time, the fundamental theorem of calculus. Fundamental theorem of calculus is a tool, is one of the most powerful tool we have. So it's an extremely powerful tool. When I mean tool, I meant something. Tool, powerful tool to evaluate definite integral. It's not a definition. It's not what the definite integral is about. The definite integral is those sums. That's the definition of the definite integral. That's really what it means. So what we're going to, the fundamental theorem of calculus is going to be a powerful tool to evaluate definite integral. It's a tool. That's what it is. All right, let's see what it states. And it's going to state this relationship between definite and indefinite. It's going to bring this up. So tell me the following. Let f be a function. And let big F be the antiderivative of little f. Antiderivative. Remember, antiderivative means that the derivative of capital F is little f. Okay? Then the integral from a to b of f of x dx. It means those sums, those Riemann sums, could be evaluated using the following theorem. It's going to be equal to the antiderivative the value of the antiderivative at the upper limit, remember that's the antiderivative of the function, minus the value of the antiderivative at the lower limit. Okay, so we take the antiderivative, we find it, we evaluate it at the upper, minus its value at the lower limit. One, as I said, it's called fundamental because it's a tremendously powerful tool to evaluate the definite integral. And then later on, we'll talk a little bit about its meaning. But for now, for me, it's just the two. I'm going to use it immediately. And if you guys are writing, keep like a little bit of an empty spot here because I want to write something in a second. So let's immediately use the theorem. So the first example, a very simple one, of course, to elaborate this. Suppose I tell you evaluate the integral from a simple one, from 0 to 1. No, actually from 1 to 4, sorry, of x squared dx. Okay, evaluate. So now it's not estimate, it's just evaluate using the fundamental theorem of calculus. So that's really my question. Evaluate using the fundamental theorem of calculus. All right, let's see what it does. On top? Beg your pardon?
What are the numbers? I can't read them that well.
Sure, 1. This one?
Yes.
The top is 4.
All right.
Okay. All right. So this theorem tells me that to find the antiderivative, that's my function f, that's my little f here, I need the antiderivative. It means I need the function whose derivative is x squared. So let us remember what's the antiderivative. I said this problem, the first one we do is the antiderivative, it means this one, the x squared dx. That's really the antiderivative. There is no limit in this case. That's the function whose derivative of x squared. Let us remember a little bit. What's the antiderivative of x squared? How does the rule work? So this is n equal to 2. It's 1 over 2 plus 1, 1/3, x to 2 plus 1 plus a certain constant of integration. Okay, so that's the antiderivative. Now, the fundamental theorem tells me that we can evaluate the definite integral by doing this. We take the value of the antiderivative. We evaluate it at the upper limit minus the value at the lower limit. So in my problem, what is f of 4? That's my antiderivative. So it's going to be equal to 1/3 4 to the power 3 plus the constant c minus. So that's the value at the upper limit minus the value at the lower limit. It means 1/3 1 to the power 3 plus c. Remember, the definite integral is a number which represents the net area under the graph. And if the function is positive, like in my case, this is f of x equal x squared between 1 and 4. So this is x squared. In my case, it's going to, since the function is positive, it's going to represent the area. So in my problem here, this definite integral is the area. So it's a number, it's not a function, it's just an honest to goodness number. So let's compute that. 4 to the power 3 is 64 over 3 plus the c minus 1/3 minus c. The c's cancel out, and I will be left 64 minus 1, 63 over 3, which will gonna give me a 21. It means the area, I'm just connecting the area here. It's not the net area, it's the area because the function is positive. That's the area here is 21. Okay, so it's a powerful tool as you realize. So the idea is that instead of taking those Riemann sums, which are tedious to do, if I know the antiderivative, and what's a big if here, then I can evaluate it by taking the value of antiderivative at the upper minus the value of the antiderivative at the lower. And now we compute. Two things. First, every time we're trying to find a definite integral, the constant c of integration end up by canceling out all the time. So when I'm computing definite integral, just to make things easy for me, I don't worry about the constant anymore. I drop the constant in the antiderivative because eventually it will cancel out. So if you keep it, it will cancel out. So since we know that, I told you that, usually don't worry about the c when you're dealing with definite integral. Just drop it. It makes the things a little bit less confusing. Now, second notation. And then I'm going to put it here. F of 4 minus f of 1. Usually we use the following notation to write it. We write it as f of x slash 1, 4. So f of x slash 1 to 4, this means f at 4 minus f at 1. So that's really a notation, no more, no less. So when I told you here to keep an empty spot, so this is equal, not equal, that's a notation right there. It's A to B, and that's a notation. From here to here, that's a notation. So when you see the notation f of x from A to B, what's meant by that is f at B at the upper minus f at the lower. Okay. Now I'm going to take the same problem again, and I'm going to do it using the notation. So that's to streamline a little bit this problem. So to make it a little bit easier, that's the way you guys will do it. So let me take the same problem again. We're going to repeat the problem just by streamlining the notation. Nothing more than that. Okay, so let me see. Evaluate the integral from 1 to 4 of x squared dx. Okay, now I'm streamlining the notation. It's equal to what? Antiderivative of x squared. So antiderivative of x squared, we should know, or because we've done this, 1/3 x cubed. Okay. And then I'm bit evaluated between 1 and 4. So that's why I'm being streamlining a little bit the notation. And that this is equal to what? This is equal to 1/3 times 4 to the power 3. You realize I didn't put constant anymore because we know it's going to minus 1/3 times 1 to the power 3. And this would give me, you can basically factor out the third, 64 minus 1. It means 1/3, 63, which is 21. And that's how we will be evaluating those integrals.
Will the constant always cancel out since it's subtracting? So it would always cancel out the constant.
The constant will always cancel out.
Okay.
Regardless how complicated this is, it will cancel out. Because when you're, it will. So that's why when I have definite integral, and I repeat, has to be definite, we don't worry about the constant. The constant will actually just make the writing more confusing. Okay. All right. Now I'm going to do two things. This integral that we did a minute ago from 0 to pi over 2 of cosine x dx, we estimated it using midpoint sum. Now we're going to evaluate it using the fundamental theorem of calculus. The fundamental theorem gives us the exact value. What do I mean by exact value? The fundamental theorem of calculus basically let the n takes larger and larger and larger value. So it gives us what we call the exact value when n is very, very large. Okay, that's what the definite integral. What we do here is just an estimate. So let's see how good is our estimate is by using the fundamental. So the question now is evaluate using the fundamental theorem, integral from 0 to pi over 2 of cosine x dx. Okay, well, let's see how good is our estimate. So it's equal to, okay, that's my function f. That's my f here. I need an antiderivative. It means I want the function whose derivative is cosine. Let us see which function has for derivative cosine. You guys remember, you should try to remember that. It's the sine of x, because the derivative of sine is the cosine. So it's the sine of x evaluated between 0 and pi over 2. That's my antiderivative. That's my f of x. Okay. Now what does this mean? It means we're taking this antiderivative and we're evaluating it at the upper limit minus we're taking this derivative at antiderivative at the lower limit. Now sine pi over 2, it's a 1. Sine is 0, 0. This is equal to 1. And now I want you to see, so that's the actual value. It means if I graph the function, so this is the cosine x function, that's the pi over 2. I graph this function, this actual area, that's because this is the function is positive, the actual area is 1. That's the actual area. But what's interesting is the following. When we estimated using the midpoint sum with 4 subdivision, look how much we got. Very, very close to the actual area of 1. So that's the actual value. This is the value when we take a lot of subdivision. And we ask ourselves, what are we getting close to? So when we take a lot of subdivision, we realize that we're actually getting close to 1. But that's our approximation only with 4 subdivision give us 1.0064, which is not a bad estimate, only with 4. Imagine if I had taken 8 subdivision, I would probably would have gotten 1.0000 something. Okay, so that's our estimate and that's our actual value. All right, now I'm going to do, of course, I'm going to practice this, but what I'm going to do now is I'm going to take the first problem we did, where we evaluated the integral by interpreting it graphically. And that's the exact value, because this time I took the actual area. I did not estimate. Now we were going to do this problem again using the fundamental theorem of calculus. So let's do that. It was the integral from -2 to 4. No, sorry. It's from -4 to 2. So I take another piece of paper. So it was the integral from -4 to 2. So more example. From -4 to 2 of 2x plus 4 dx. And this time I'm going to do the problem using the fundamental theorem, and then we're going to compare to see if we're doing well. And this one I have to be, I'm going to do it slowly. What do I need? I need the antiderivative of this function. That's really what I need. Now, what's the antiderivative of this function? 2 is a constant. Antiderivative of x is a half x squared plus. So now I'm in the process of evaluating the antiderivative. Plus, what's the antiderivative of 4? What's the antiderivative of 4? Start remembering. I want answers on the chat, because this is we've done. So antiderivative of 4 is 4x. So this is my antiderivative. That's my f. And this has to be evaluated between -4 and 2. Okay. Now, before I do that, I definitely will simplify this piece. 2 and 2 cancel each other. So I'm going to end up with x squared plus 4x evaluated between -4 and 2. This is the antiderivative. That's the antiderivative. So if I, basically it's easy, because if I find the derivative of x squared plus 4x, it's 2x plus 4. Okay. Now we evaluate. So really, what the fundamental theorem of calculus is boiling down to be able to evaluate the definite integral, I need an antiderivative. So that's we're going back to the idea of antiderivative. If I can do that, I can evaluate. If I cannot do that, I don't know what's the antiderivative easily, then we go back and use the Riemann sum. That's really what the idea is here. So finally, now let us evaluate. So it's the value at the upper minus the value at the lower. Let's evaluate at the upper. Means I plug in 2 for x. That's going to give me 2 squared plus 4 times 2. That's the upper value. And here I will get minus 4 squared plus 4 times minus 4. And now I evaluate. I will have here 4 plus 16, 20, minus. That's going to give me a 16. And 16 minus 20 give me.
Wouldn't
Of course, I did a mistake.
Wouldn't the 4 times 2 be 8?
Yeah, so equal to 4 plus 8. I'm allowed to do this mistake, you're not. 4 plus 8, it's a 12. Minus. Am I goofing here? That's going to give me a 16 minus 20. I'm doing something stupid. Something I don't like.
It's 16. 4 times negative 4 should be 16, not minus 20.
What?
4 times negative 4, it goes to
minus,
negative 16.
Something else is bothering me. It's going to give me 0. Give me 12, right?
Yeah.
Did I get 4 over there? That's x squared plus 4x. 2 squared plus 4 times 2. That's it, 12. Minus. That's correct here. I'm getting 12. If I get 12 here, why did I get 4 here? Because nobody corrected me here. That's going to give me 4, and that's going to give me 2. That's 16. Okay. We definitely have to get right. So my what was bugging me, why I got 4 here and I'm getting 12 here, it should not be the case. So here it should be, the answer should have been 12 in the geometric interpretation, because you guys should have corrected me here. So this is going to give me 2 times 4, which is 16, minus 4 plus 16 equal to 12. And definitely the integral is equal to 12. We definitely have to have the same answer. Okay. All right. Now we're going to just practice those. So we're going to do several problems where we're going to, at least one problem where I need to practice this definition. So now no interpretation, because we did the interpretation. Now just evaluate using the fundamental theorem of calculus. So I'm going to give you the following: integral from 1 to 4 of 3 over x. Now simple evaluation, just drill problems. No more, no less. Dx. Okay, as I said, those are drill problems now. So this is equal to what? We need to find the antiderivative of this function. Now the antiderivative of 6 is easy, we know it, it's 6x. The antiderivative of 3 over x, so let's remember how we do that. 3 over x is 3 times 1 over x plus 6 dx. Okay, and now we're ready to find the antiderivative. So let's see what's the antiderivative, and we're going to evaluate it between 1 and 4. So first I prepared it. 3 is a constant. The antiderivative of 1 over x is ln of x plus 6. Antiderivative is 6x. So once I know the antiderivative, the rest is equal to antiderivative at the upper minus the antiderivative at the lower. At the upper, I will have 3 ln of 4 plus 6 times 4. At the lower, I will have 3 ln of 1 plus 6. So finally, I'll get 3 ln of 4 plus 24 minus ln of 1 is 0, so minus is 6. So I end up 3 ln of 4, 24 minus 6, which is going to give me 18. Okay, so those are just a drill problem to be able to apply. Okay, I will do, I guess, one more. Again, those are just evaluate. I'm trying to remind you. So my goal now is to remind you how to find those antiderivative. 2 to 5, that's a definite integral. 4 over x squared dx. Okay. Now, we can use the property sometimes in antiderivative. 4 is a constant. I can actually pull it out if you want, make things a bit easier, times the definite integral. From 2 to 5, I will be left with 1 over x squared dx. So what I did, that's a constant, and we know that we can get the constant out. Now I need to find the antiderivative. Now how do we find the antiderivative of 4, 1 over x squared? So now I'm preparing, so you guys remember, 1 over x squared, to find this antiderivative, I have to rewrite it as x to the minus 2. I'm going to assign a lot of problems for tomorrow. Please do them because it's a good way for you to remember how to find antiderivative. So it's 4 times between 2 and 5. Now, what's the antiderivative x to the minus 2? Remember the rule. Antiderivative of x to the n dx equal 1 over n plus 1 x to the n plus 1, as long as n is different from minus 1. Okay, and if you have minus 1, it's the ln. So in this problem, in this particular problem, my n is equal to minus 2. Okay, so it's going to be equal to 1 over minus 2 plus 1 x to the minus 2 plus 1. So it's equal to 4 times minus x to the minus 2 plus 1 is 1 over x evaluated between 2 and 5. So finally equal to 4 times the value at the upper limit. It means minus 1 over 5 minus the value at the lower limit is minus a half. And this will leave me with minus a fifth minus minus plus a half. And finally, just to be complete, I can find a common denominator, and then I will have minus 2 plus 5, minus 2 plus 5, which is going to give me a 3. So the answer would be 12 over 10. Okay. And geometrically, I try this integral, so that's its value. And geometrically, this integral represents the following. If I draw the function 4 over x squared, that's my limit. This is 2, and this is 5. As I sketch this function, which is a decreasing function, so this is the function 4 over x squared. The area under this graph, that's positive function, the area here is the 12 over 10. And that's the actual area. Because always remember that this definite integral is nothing more than the sum of the area of those rectangles. That's really what the meaning is. The fundamental theorem, which is mathematically we can prove it, is this tremendous tool that I can compute that area without really having to estimate, as long as I know the antiderivative. As long as I know the antiderivative. Okay, I guess that's it for now. Please make sure you do your homework for tomorrow. Absolutely, it's crucial. So you practice how to use the definite integral and how it help you to remember the antiderivative idea. And of course, as usual, tomorrow you're going to have your regular quiz, and I will tell you on Brightspace what is it about. Okay. Any questions before we proceed? I mean, before we quit. Any questions? Okay, bye-bye. Please do your homework. Bye-bye for now.
Have a good day.